This is APAB Calc. We are doing 2.6, which is related rates, and we are on the fourth video in this series. So we're now entering the dreaded cone problems. So what makes a cone related rates problem tricky is that it's by definition going to require an auxiliary equation every single time. And we touched briefly on that in example 5 when I made my life much harder than it had to be. But with cone problems, you have no choice but to use an auxiliary equation. At one of two different points in the problem, there is one point where if you use it, it's going to make your life a whole heck of a lot easier, and there's another point where if you use it, it's a bit late to the game, and it'll still be necessary and required, but it's not really going to help you as much. So let's walk through some cone problems. So the first thing we should talk about is that it's helpful to know the volume of a cone. It's one of the few shapes that you really should, one of the few like 3D shapes that you should really know the volume of. Going into a calculus test. Sometimes the AP Calc test does you a solid and gives you the formula for the volume of a cone, but it is best to assume that they will not. So you have two different kinds of cones. They're the same cone either way. I did a terrible job drawing it, but so one of them looks kind of like those cups you get at the doctor's office, and the other one looks sort of like a party hat. They're the same cone. It's just that this one's usually called an inverted cone because usually we're talking about the point being up. So a cone has a radius at the bottom because the base of the cone is a cylinder, or a radius at the top if it's an inverted cone, right? And then it has a height. Now these are both right cones, right? They're not, the height's not on a slant, but we're going to assume that we're always dealing with a nice happy right cone. So they have a height that comes directly from the center of the circle up to the vertex of the cone, right? Up to the PV cone. The volume of a cone is 1/3 pi r squared h, okay? One way to think about this is if you picture a cylinder, right? So a cylinder, we're going to go over here for a sec. A cylinder like a soda can, right? Okay, a cylinder is actually two circles of the same radius, right? Two circles of the same radius, and then it has a height. It has a volume of pi r squared h, which makes sense because if you think about it, the base is a circle, pi r squared, and then it's like stacking CDs, right? You're multiplying by the number of CDs, right? H is how many CDs. So the area of a CD times however many CDs you stack. The reason I mentioned this is because when in doubt, if something is pointy, its volume is 1/3 of the non-pointy version. So see how this is the version that has a circle on both ends? Well, if you make it pointy instead, it's going to have 1/3 the volume. There's a whole bunch of logic for why, but it's a helpful way to kind of keep an eye and memorize this. It is also worth knowing the volume of a cylinder. That does come up occasionally, but not really as often as a cone. So let's talk about cones. Cool. So when we talk about these cones, there are actually two cones in each problem. There's the cone that is usually some sort of a fixed shape, and then there's the stuff that's usually contained in the cone. Now that's not quite going to be true in P6. P6 is a pile of gravel. It's not going to be a fixed shape. But basically what happens, and we'll walk through this in E6, is that pretend you're going to the doctor's office and you get one of those little pointy, triangular, or conical rather, cups, and you fill it with water. The cone is, like the cup is a cone, right? It's a cone of a fixed height and a fixed radius. But inside the cup is a little cone of fluid, right? The water is also a cone. And as you drink water, that cone gets smaller, right? Because the water level drops. So that cone essentially is going to end up having a proportional height and radius to the height and radius of the original cup, like the actual fixed cone. So let's walk through E6 and I'll kind of show you what I mean, okay? What makes cone problems tricky is you're always going to need an auxiliary equation. Part of the reason you're going to want an auxiliary equation is because if you look, when you differentiate this is a product rule. And nobody wants to do a product rule with R's and H's and V's and T's. It's not going to be fun. All right, so a tank in the shape of a right circular cone with an altitude of 8 meters and a base radius of 3 meters is being filled with water at a rate of 3,000 liters per minute, which they tell us is 3 meters cubed per minute, which is relevant because everything else is measured in meters. So we want to use, despite the fact that they gave us that 3,000, everything else is in meters, so I don't know why they bothered to give us that. We want to use the 3 meters cubed per minute. Okay. How fast is the surface of the water rising when the depth is 5 meters? Okay. So, what we're looking at is that cup from the doctor's office, okay? Here's what we know about this cone, the actual cup. The cup has a height or an altitude of 8 meters, right? And it's not a cup, I mean, it's huge. 8 meters is not small. And it has a radius, this base of the thing, even when it's at the top, it's still a base, is 3 meters, right? The base is 3 meters. And then it's being filled with water. So I'm going to use, I guess we'll do, well, I think I have like aqua, so we'll use aqua. Okay, so in this, there's water, And this water level has its own height and its own radius. But because the water level is changing as the water rushes in, right, so dV dt, the rate at which the volume is changing, that's how fast the water is rushing in. And if you're not sure that it's dV dt, look at the fact that it's measured in meters cubed, right? Volume is measured in linear units cubed, is a positive 3 meters cubed per minute. The reason it's positive is the volume is increasing, right? The water is going in, right? Water's going in. Okay, so what's going to happen as that water goes in is that this height is going to get bigger, and the radius is also going to get bigger, because as you can tell, the water's going to fill the cup, and as the height gets bigger, the radius also gets bigger. So their question is, how fast is the surface of the water rising when the depth is 5? So what they want, right, what they want is dHdt, because that would be how fast the surface is rising, it would be that change in the height, when h equals 5, okay? That's the thing we want. So here's the problem. As soon as you see it's a cone, this is your equation. But if you notice, they never mention the radius at all, right? Other than to tell us that the radius of the whole tank is 3, they don't mention the radius at all. So the issue is that I definitely want to use this equation, but we know nothing about R. So what we want to do is we want to look at the big triangle created by the entire tank, which has a ratio of 8 meters to 3 meters. And we want to look at the similar triangle, right? Because see how they share this angle at the bottom? So this angle at the bottom, we want to look at the similar triangle of R and H, right? And then we're going to get this auxiliary equation. So we're going to get an auxiliary equation that tells us that R is to 3 as H is to 8. Now the thing I want to replace is R, so I'm going to solve for R and get that, sorry, that's not what I meant to write. I'm going to get that R is 3H over 8. The reason I want to solve for R is I want to replace R. Now that seems counterintuitive, because you're thinking, oh, but I want H stuff, so I should solve for H, but you want to replace R so that your equation only has H stuff. So I'm going to use this to replace my R squared. And what's going to happen as a result of this is I'm no longer going to have to do that stupid product rule. So I'm going to get a 1/3 pi. R squared is going to be a 9H squared over 64, right? Because it's 3H over 8, whole quantity squared, times an H. If I clean this up, I think I can cancel one of these 3's, and I get 3 pi over 64 in front of an H cubed. So now I have a super nice equation. So now, right, now the equation that I'm dealing with, my new equation, is volume equals 3 pi over 64 H cubed. And that's a lot nicer because there's no need for a product rule. I'm going to walk you through what happens if you don't spot this in a second. No matter what you do, you have to get this equation or you won't be able to do the problem. Like, you need the auxiliary equation for a cone problem. Every cone problem, no matter how good you are, there's not another trick. You have to see the auxiliary equation. If you see it earlier and replace it before you differentiate, you're going to have a much easier time. If you see it after you differentiate with the product rule, you're going to have to differentiate this too and then replace some R stuff, and it's going to be kind of a pain. So, when I differentiate, I get dV dt, which is a quantity I know, because I know how fast the water is rushing in, equals a 9 pi over 64 H squared dH dt. Well, the thing I want is dH dt, and I think I know everything else. I know dV dt is a 3, and I was told when H is 5. So, I get, when I substitute my specific stuff in, I get a 3. I'm going to go ahead and multiply the 64 over and divide the 9 pi over. I'm also, this H squared is actually going to be a 25, right? So that's going to, well, I'll leave that there for now, and then we'll divide it over in a sec. When you clean this up, you seem to get a 64 over, when I divide the 25 over, so I canceled this and got a 3. When I divide the 25 over, I'm going to end up with a 75 pi on the bottom, and that'll be my dHdt. The last thing I need to do is make sure I have my units, right? When I answer the question, height would be measured in whatever the linear units of length are here, which in this case is meters, and time was minutes. So I'm going to get 64 over 75 pi, note the pi is on the bottom, meters per minute, and that's my answer. So again, you need that auxiliary equation. Now I do just want to show you what happens if you try to differentiate this without plugging in first. So if you had done that, right, if you tried to do that without plugging in first, just to show you what this looks like, v equals 1/3 pi r squared h. So this would be my u, and the h would be my v. So, which I know is confusing because of v for volume, but I mean v for the product rule. So my dv dt would be u dv plus v, and then du is going to be a 2/3 pi r dr dt. So here's the problem. You'd get this, and then when you go to substitute, what you're going to realize is that you want this, you know this, you know this. You are missing these guys and these guys. So you'd still need this auxiliary equation to find them, right? So when you realize that you're missing the r stuff, you would realize, oh, hey, I need this equation anyway. And so then you would have to set up something like r equals 3/8 h, which means that at h is 5, your r would be 15/8. So you'd have to plug 15/8 into these spots. And your dr dt would be 3/8 of dh dt. Sorry, that's not what I wrote. dh dt. So then you'd have to so you would plug in 15/8 here and here, which is no fun. And then for this dr dt, you'd plug in a 3/8 dh dt. And you can see how it gets much, much worse. It will land you at the same spot in the end, but it's not pretty. So when you see a cone problem, you really want to identify that auxiliary equation. And sometimes it's this similar triangle thing. Sometimes it's actually given to you, which I think is what you're going to find in the gravel problem that we do next. Okay, so again, I would not suggest differentiating with the product rule on these cone-related rates problems. I would suggest that your much better plan is to find that auxiliary equation first. Okay, so we're going to do P5. I'm going to read it out. Excuse me, I'm going to read it out loud to you, and then you can, oh, sorry, P6, my bad. P6, I'm going to read it out loud to you, and you can pause me whenever you're ready. All right. Gravel is being dumped from a conveyor belt at a rate of 25 cubic feet per minute, and it forms a pile in the shape of a cone whose base diameter is twice the height. How fast is the height increasing when the pile is 12 feet high? Cool. Pause me if you want. So there's like some conveyor belt thing, right, and gravel's dumping off of it, and it's dumping into a shape of a cone, right? So here there isn't some like here there's no like cone inside a cone, right? As the cone gets bigger, like it started out as a tiny little cone and then it got bigger and bigger and bigger as the gravel dumped. Here's what we know. We know that this is the height and this is the radius, right? We know that dv dt, the rate at which the volume is changing, is a positive 25 feet cubed per minute because we were given the rate at which the stuff's coming off the belt, right? And what they want is dh dt when the height is 12, okay? 12 feet. Now, that's what we want. So here's the problem. You can't get an auxiliary equation from similar triangles because there is no internal other triangle. You're not like filling this. This isn't like a fixed shape of a cone that's getting filled up with something. This is a cone that is just a pile of gravel. The whole pile gets bigger. But because of that, when you have a problem like this, they're usually going to have to give you some sentence in the problem that actually tells you what the auxiliary equation is. And here it is. A cone whose base diameter is twice the height, right? So what that means, okay, is that the base diameter, which is the same as double the radius, right? This would be, because this is the diameter, right? That diameter is apparently twice the height. Well, that means that my auxiliary equation is 2r equals 2h, or better yet, r equals h. That's the auxiliary equation we want to use. So now, when we write our equation, we know, hopefully we memorize that the volume of a cone is 1/3 pi r squared h. And now we say, oh look, I don't know anything about r, but I want h stuff. Conveniently, r is just h. So my volume is actually 1/3 pi h cubed, right? Because instead of r squared, I put h squared, and that's an h cubed. When I differentiate, I get dv dt equals, the 3 drops down in front and is gone, so I just get pi h squared dh dt. And I know all of these things, right? I know that dv dt is 25. Pi h squared would be 12 squared, so it's $1.44. and then dHdt. So I just divide by the 144 pi, and I get that my answer is 25 over 144 pi. H would be measured in feet in this problem, and time is in minutes, so feet per minute. That's my answer. Okay, cool. So that's our P6 and E6. All right, we're going to keep moving forward. Last examples, we're going to do what we call trough problems, and then that'll be it for our related rates section. All right, cool. Trough problems. Now, I don't think you're super likely to see a trough problem on the AP, but we're going to walk through it anyway. So I grew up on a farm, so I'm familiar with what a trough is, but I know that not everybody is. So I'm going to walk you through what a trough looks like, and we'll go from there. So the cross-section of a water trough is an inverted isosceles triangle with its top edge horizontal. Okay, so here's what a trough looks like. A trough is like the thing that animals drink or feed from in a barn, right? Or in some sort of a pen. So what it looks like is it's essentially a prism, right? Okay, so it's a prism. It has two of the same base. This is the base, okay, and it's got the same base over here, and then it's got parallel lines that run between it, and so the top is open, right, and because this is triangular at the bottom, to be honest, it would probably be hanging from something because I can't imagine it standing, but basically the water, this top piece is open, and the animals walk up and eat or drink from it. So that's what a trough is. We're told what the cross-section is. It's this isosceles triangle. I did a bad job drawing it, but because it's isosceles, these two sides are the same, right? Again, terribly drawn by me, but it is what it is. The triangle has a base of 2 meters and a height of 1 meter. So this base is 2 meters, right? And they're saying that this height is 1 meter. Now, this is going to be the same problem that we've seen with the cone, where the trough doesn't have to be full. The trough is a metal or a wooden or whatever thing. It's probably metal. But the water in the trough, right, the water in the trough is only going to fill up to a certain level of the trough, right? And as the animals drink, that level will actually drop. So there's this other, like, essentially trough shape that is inside the trough that is the water. Does that kind of make sense? I'm hoping it does. I don't know why I asked that like I'm not talking to a video, but it's cool. All right, the trough is 5 meters long, so what they mean by that is that this length is 5 meters, okay? Now, water is being pumped into the trough at a rate of 60 cubic meters per second. How fast is the water level rising when the water is 40 centimeters deep? And that's a big heads up, like just a thing to watch out for, be real cautious. Every other unit was meters, and this is centimeters. So you want to make sure that you use H is 0.4 meters, because if every other unit was meters and suddenly they threw you a centimeter, that's a trap. All right, cool. So let's figure out how to do this. The first thing is that this is not an easy formula to memorize the volume of, okay? In the sense that you have to logic through it. So this is sort of that same idea as the volume of a cylinder that we just discussed, where you have one shape and then you have a number of those shapes all stacked next to each other. The area of this triangle, so the volume of a trough, is essentially the area of the triangle, right, the area of that base, times how long the trough is, which in this case is a constant, right? This is the length of the trough, right? Because you've got one of these triangles and then another one, and you've got like however many triangles, you're going to times it by the length of this thing. So essentially, the area of that base, right, I'm just call AB for area of base, right? So that's the volume of the trough. So we need to look at what this base looks like. Remember, we don't actually care about the volume of the big container. We care about the volume of the water in it. So here's what we know. We know that there's a base and there's a height, and that the area of a triangle is 1/2 base times height, right? That's what we care about. Okay, so that means that the volume of this thing, if I'm trying to make an equation, the volume of this thing is 1/2 base times height times 5, or 5/2 base times height. Now, the same problem that we're going to run into is if you wanted to differentiate this, this is totally a product rule, and that should be a big red flag that you don't want to do it, right? It's a product. So the trick is that we probably need an auxiliary equation, right? We need another one of those proportional triangles kind of situations where we can say, oh, wait, there's an auxiliary equation because I need to replace the base. The reason I say I want to replace B is if you look, none of the questions ask about B. They ask how fast is the water level rising, right? The thing that I want is dH dt when H is 0.4 meters, right? I want stuff that involves H. At no point in the question was B mentioned, but I still have this base. So what we're going to have to recognize is that these triangles share the same angle down here. And this one has a base of 2 meters and a height of 1 meter, which means I can make my auxiliary equation to be that height is to 1 meter as base is to 2 meters, meaning 2 times the height is my base. There's your auxiliary equation. So now, when you use that auxiliary equation to replace, you're going to get 5 halves instead of base. You're going to use 2 height times height, right? That's going to equal your volume, right? So I replaced the base with 2 times the height. So I'm pretty sure my equation ends up being volume equals 5h squared. Well, now it's pretty easy to differentiate. dV dt is 10h dH dt. And now it's pretty easy to plug in, right? I know dV dt. I also forgot to label that on my diagram. Sorry, I'm the worst. Going into the trough is water at a rate of 60. So dV dt is 60 meters cubed per second. Okay, so I now know dV dt is 60. That's going to equal 10 times the height, which is 0.4. Oh, that's so nice of them to take care of the decimal problem for me, times dH dt, right? So it seems to me, so that's my substituting, right? So it seems to me that I get 60 equals 4 dH dt. So I get 15 equals my dH dt. When I answer my questions, h was measured in meters and time was in seconds. So I get 15 meters per second. That's my answer. Okay? So again, with the trough problems, you have to, there's no prescribed easy formula. You kind of have to picture that essentially to figure out the volume, we're multiplying the shape on the end by the length of the entire trough. So you're going to try P7. I'm going to erase E7, and then we'll go from there, okay? All right, so I'm going to read you P7, and you can pause me at any point and go ahead and try the problem. A water trough is 6 meters long, and its cross-section has the shape of an isosceles trapezoid. Sweet. That is 30 centimeters at the wide at the top, and 30 centimeters, something went wrong. 30 centimeters wide at the top, 30 centimeters wide at the bottom, 80 centimeters wide at the top. That's weird. And 50 centimeters high. I think it wasn't supposed to have this. That doesn't seem to make very much sense. Yeah, I think it's not supposed to have that. So, a couple of things to be careful about. See how this is meters, and see how this is cubic meters, but these are all centimeters. So when we draw it, be careful to convert these guys. Be careful to convert these guys to meters. Okay. Sorry about the weird extra word that appears to be there. I'm unclear on how that happened, but it is what it is. All right, so let's walk through our P7. Okay, so here's what's happening. We have a isosceles trapezoid. Okay, it's wider at the top, right? So this is 80 centimeters, so 0.8 meters, right? And it's 0.3 meters at the bottom. Again, I don't know where that extra thing at the top came in. That doesn't make a lot of sense. And the height of this thing is 0.5 meters, right? And then there's this whole trough length, right? Okay, I'm bad at drawing a trough, but you get the gist. Okay, cool. So it looks like this. Okay, so the whole trough length is 6 meters, right? Okay, so to do this, you kind of have to know the area of a trapezoid, right? So the area of a trapezoid, well, I'm gonna argue you might not have to. Let's walk through and see. I will tell you that the area of a trapezoid is 1/2 the height times the sum of the bases, but we might not need that. We might be able to be a little bit clever about it. Okay, so in this, we have water, right? And the water is going to fill the bottom part, okay? So a couple things to notice, because this is an isosceles trapezoid, right? So this right here, the whole thing at the top is 0.8, but because 0.3 of it is being used, essentially 0.3 of it is being used in the middle, right? The two sides have to be whatever's left over from 0.8 minus 0.3, which would be 0.5, cut in half. So 0.25 on this side and 0.25 on this side and 0.3 in the middle would be how we get that 8 meters, right? Or 0.8 meters rather, right? So the volume of this, so this is the area of this one side, and it is going to matter, but we're gonna work from there. So this base of the trapezoid is going to be 0.3. But the question is, what's the other base of this trapezoid, right? What's the other base of this trapezoid? Well, the middle part's a 0.3, but I don't know what these two parts are, so I'm going to call them x's, right? So this base 2 is essentially 0.3 plus 2 of these x's, right? So the issue I'm going to run into is I'm really going to need to be able to find essentially an auxiliary equation that allows me to deal with that x, okay? And I have a height right here. So the trick here is that the volume of this thing, if I write the entire big equation, the volume of this thing is going to be 1/2 the height. Sorry, I didn't put volume equals. Right, so 1/2 the height, and then the sum of the bases are going to be a 0.3 plus a base 2, right? The other base I don't know, this blue base 2, times the 6 meters long trough, right? So if I clean that up a little bit to start, I can at least put the 6 with the 1/2 and make this a 3h times 0.3 plus b sub 2. But the issue with b sub 2 is I just don't know, I don't know anything about it, right? So what I need to do is I need to look, I'm going to zoom in at this triangular shape, because what I actually have here are similar triangles. This is a 0.5 meters, this is a 0.25 meters, and the little water triangle is an h and an x. They're similar, so essentially h is 2.5 as my x is 2.25, right? If I multiply everybody, the easiest thing to do is just multiply everybody by 4, because that'll get rid of all those, I take it back. Sorry, my brain dies sometimes. It's been a long day. 0.25 h equals 0.5 x. If I multiply everybody by 4, I get rid of all my decimals. So I'm going to get h equals 2x, right? And that actually makes a lot of sense, because if you look, this height is double of this x. Okay, so the reason that's useful is, if you notice, I figured out that that base 2 was actually 3 plus 2x. So I could replace base 2, 0.3, with 0.3 plus h. And that's going to solve my problem of needing an auxiliary equation. Again, these trough problems are really hard. Don't panic if you're hating this. It's completely normal. I don't think you're going to see a lot of related rates problems that are this difficult. 0.3 plus h. So you're going to get a 3h times 0.6 plus h, which is going to be a 1.8h plus 3h squared. So now I have this nice happy equation. Notice that most of the work was before I did any calculus. I haven't differentiated, so I actually haven't done any calculus at all. Oh, I did forget to label my dv dt, which is that the rate is coming in at 0.3. It's positive because the water's coming in, meters cubed per minute. Okay, so now when I differentiate, right, so all of that work was before any calculus. And this is when I say, like, the algebra skills and the trig skills are really what get you. So my dv dt is going to be equal to 1.8 dh dt plus 6h dh dt. And the thing we want is dh dt, right? We specifically want dh dt when h is 0.25 meters, right? So I'm just going to go ahead and plug in those values, right? So when I substitute, I'm going to get 0.3 equals 1.8 dh dt plus the 6 times the 0.25, right, which is going to be a 1.5 dh dt. So I'm going to get 0.3 equals 3.3 dh dt. So 0.3 divided by 3.3 is a 1 over 11. And that would be meters for the height and minute for the time. So there's my answer. All right, so again, I know that these are really hard. There's a reason that we built to this level of difficulty. Honestly, what I expect you to see most of the time on an AP in terms of related rates is probably something that uses Pythagorean theorem, maybe about 2 cars traveling in different directions, or 2 boats traveling in different directions, or a ladder problem. I don't think you're going to see something as difficult as a trough. I do think that you're likely to see a cone at some point. Maybe not on your actual AP, maybe on some of the practice material I give you, but you'll probably see a cone at some point. I can't remember the last time I saw a trough problem on anything that was an actual released AP. That doesn't mean it doesn't exist, but it does mean that if you feel like these were really difficult, it's okay, because the problems were supposed to escalate in difficulty, and they did. Okay, so that's our 2.6, and that's the end of our Chapter 2 work. We do actually throw L'Hôpital's into Chapter 2, but that's not actually in Chapter 2 of your textbook. So we're going to include it in the Chapter 2 lessons, but it's not actually in the Chapter 2 of your textbook.